AI, and the future of autonomous systems. Please welcome our panelists. Bill Vass, CTO of Booz Allen Hamilton, Eric Breckenfeld, Director of Technology Policy at NVIDIA, and Lawrence Walter, CEO of Code19. The conversation will be moderated by Billy Mitchell, editor at Fed Scoop.
All right, good afternoon, everybody. As that wonderful voice of God said, I'm Billy Mitchell, executive editor of Scoop News Group, and it's my pleasure to be joined by these fine gentlemen. Once again, Bill Vass, chief technology officer of Booz Allen Hamilton, Eric Breckenfeld, director of technology policy at NVIDIA, and Lawrence Walter, co-founder and CEO of Code19 Racing. I'll give them an opportunity here in a moment to give a little bit more background on who they are, and they've all partnered together in some various ways, so you can touch on that a bit. But just to give you a sort of synopsis into what we hope to accomplish here today a little bit, we're looking to explore physical AI and how it's transforming autonomous systems across defense and racing, two very disparate things, and I can't wait to help connect the dots on those for the audience, because I was a little curious myself when I got asked to do this. Why are we talking about racing and defense? What do those things have in common? It's pretty interesting. And then examine the technical, regulatory, and security challenges that goes along with deploying all those things together. So, Bill, I'll start with you. Give us a little background on who you are, what you do, and how you kind of came to be here in this panel with these other gentlemen.
Yeah, so I'm the CTO for Booz Allen, and we do a wide variety of technology, but a lot of autonomy and high-performance computing and AI and satellite systems and other things like that, along with quantum technology. I came from AWS about a year ago, where I also worked on autonomy and robotics and quantum computing and other things like that, but I also ran an autonomous systems company called Liquid Robotics, which was a startup that got sold to Boeing. So, and there they did a lot of defense work as well. So a lot going on in that space.
All right, Eric, you're next.
Yeah, thanks for having me. Eric Breckenfeld, I'm the Director of Technology Policy at NVIDIA. Obviously, at NVIDIA, we're very involved in the autonomy simulation space. I think we'll get into a little bit more later what the specific computing needs of those spaces are. But really, I work with lawmakers, staff inside the government, places like DARPA, Department of Energy, who are trying to understand how to adopt AI solutions into the various problem sets that they experience. Before joining NVIDIA, I was actually working as a subject matter expert at DARPA, oddly enough through Booz Allen, although did not come into contact with Bill at that moment, but was involved in a number of autonomy programs when I was at DARPA. The Subterranean Grand Challenge was going on when I was there, which was a very exciting autonomy program as well. So really excited to be here.
Awesome. Lawrence, you're the interesting one with the racing background. What's your background, I guess, but how do you make it into this panel we're talking about physical AI, autonomy, and really, some defense element. What does racing have to do with it?
Yeah, so I'm the CEO, co-founder of Code19 Racing. My personal background, I spent over 20 years in the United States Army, Army Intelligence. And we formed Code19 Racing as the world's first professional autonomous racing team. So we take Formula One race cars and pack it full of the sensors and technology and build, AI systems that can compete against the best teams in the world for that trophy and that claim to be the fastest AI on the planet. And if you look at the sport of autonomous racing, really inspired by what happened at DARPA and other places, and adversarial multi-agent racing really is one of the top grand challenges, unsolved, wicked hard problem. And so for a small startup to be able to take that on their own is very difficult. That's why we partner with companies like NVIDIA and Booz that can apply all of their expertise to help us be successful on the track, and then look for ways to commercialize the technology that's coming out of that to support the warfighter and to support the mission of all the great people in the DoD.
All right, so that sets the stage. We know our panelists a little better. We talked a bit beforehand, and the thing we kept coming back to was this concept of the three-computer problem. I think we're going to spend most of our conversation tying back to that and then trying to tie things together between the defense and the racing space. But let's start with that three-computer problem. What is it?
Yeah, so for the longest time, we've been doing autonomy with a two-computer problem, right? And basically, you did a lot of autonomous training in the cloud, and then you always had to have something that ran on the device because you've got low latency and the ability to operate when there's no network. What's changed is with AI and the Gen AI capability is that third computer is now there. And then folks like NVIDIA have really advanced the simulation tech as well. So basically you have the first computer, if you like, is the actual simulation that you're running in the cloud. The second computer is the autonomous training engine, like the H200s and stuff that are pointed at that, looking at that, if you like, and learning from it. And the third computer is once you've done the inference engine, you load it on the vehicle so that it can operate. Now, the vehicles don't necessarily operate completely disconnected from the network either, so they can still connect back to the second computer in the cloud potentially, but you can't rely on that due to latency, or like in the Department of Defense, you're going to have network-defined environments, so you have to continue to operate independently, autonomously during that. So it's those three computers working together, one running the advanced simulation, which is getting to be harder and harder to simulate the full physics and rendering of the real world. The second one is the learning engine, if you like, the brain that that's watching and learning. And the third one is the execution brain that runs on the device.
Interesting. Eric, tell me about how NVIDIA is working to figure this out, how to promote it and give a better understanding and make this more prevalent.
Yeah, absolutely. So when you look at these three different computing needs, obviously you would imagine they would prescribe vastly different infrastructure needs, vastly different support needs. And I think Bill's explanation was a great way of looking at it. I might look at it a different way, where I might say, that first computer, that's the AI model brain, that's analogous to what we're already very familiar with that's happening in data centers, right? AI data centers that are training large models. They don't have to be large models, but often large models. That's in this three computer framework, that's the computer that's downstream from these very large installs that we'd all be very familiar with. And so that's a space that we're accustomed to supporting. Most of the investment right now that's going into the AI space is going into infrastructure that supports that computer set. If I scale all the way down, I'll go in a strange order to computer 3. This is the computer that lives on the edge. This is downstream from all sorts of edge applications of electronics that probably really got a shot in the arm in the mobile device era, but we're using learnings from drone autonomy, from more conventional vehicle autonomy. There are lessons learned, and there are infrastructure support processes that can support that. Now there's this middle model, this second model, this simulation space. This is the one that honestly is most downstream from an area that NVIDIA is actually quite familiar with, which is the
video games.
Gaming and video rendering process. Yeah. But it's a lot more challenging than that, because we no longer want just wire mesh models. Now we want physics to a very high degree of fidelity to be embodied in these models. We want materials properties. We want, in some cases, chemistry, fluid dynamics, things like that may not have been in your circa 2009 video game, but that we now desperately need to make these simulations actually useful.
Wow, that's incredible. Lawrence, how does this connect to what you're doing with Code 19? The three computer problem, is it something you're experiencing, and how are you grappling with that?
Well, racing is a risky business, right? And when you're dealing with million-dollar race cars, multi-million-dollar race cars, and you're pushing those vehicles to get the most performance out of them possible, accidents happen, right? And when those accidents happen, it's very costly. And so it's critical for us to get the most performance out of our AI agents to be able to test as much as possible in a simulation environment. And it can't just be, the path planning and the obstacle avoidance. It's got to be all of those things that you talked about, right? The track surface model, like all the environmental variables, all the things, what the opponent's doing. All of those things we've got to run simulations as much as possible, so that when we are on track, when we are testing, or when it comes time to race, that we've tuned the parameters and tuned the model and tuned our AI agent so it can be as performant as possible. And I think there's a lot of racing is different to defense, but if you think about like mission critical on the racetrack is very analogous to what you have on a battlefield, where it's not crashing the vehicle into a wall. It's like somebody actually losing their life or some other kind of tragic mistake or problem, or you lose the battle, right? So what we're developing on the racetrack with NVIDIA, with Booz, and our ability to do that very quickly, so that we can get the most out of the vehicle, the most out of the track time that we have. It's critical. Simulation is critical.
Yeah, no, that's interesting. Let's push on that a bit more, because I think there are, it's not apparent when you're watching F1 on your TV that, whoa, that could be applicable to fighting a war or saving someone's life in a combat scenario. But as you mentioned, it is a matter of safety, efficiency, life and death, things that all matter to the Department of Defense as well. So Bill, I'll come back to you. As you heard what Lawrence just said, help connect the dots a bit more. What he's doing? How is what he's doing applicable to what some of our services are doing with?
Well, I mean, it's very in the automotive world. You test your designs and environment in the crucible of motorsports, as they would say, and the reason is the speed. Autonomy at speed is very hard, right? It's hard at any speed, but at the racing speeds or at aircraft speeds, it's extremely hard. And so high-speed autonomy, that low latency, and then the other component is, if the network goes down while he's racing, he's got to keep racing. And same thing's true with the Department of Defense. So the ability to have the physics capability that you deal with, and that's one of the reasons like DARPA sponsored the Pikes Peak Challenge, because doing autonomy slowly is something that we're getting better and better at, right? But a robot vacuum or whatever. But doing autonomy fast is a big defense problem, right? Whether it's, like I said, aircraft or missiles or autonomous vehicles in the battlefield have to move fast, right? So I think that's where all of the challenges of friction and managing the local compute, sensors. I mean, I have my Formula One racing license, so I always, Lawrence and I talk a lot about that seat of the pants feeling when you're on the track, and how do you pass that to an AI agent, and how do you get the human capability into the autonomy. And that's true in flying a jet, that's true in the battlefield, that's true in driving the tank. And so that's where we connect the dots. In addition to that, it's someplace where we can demonstrate outside of the, if you like, the classified environment. Yeah. And we really show everything that we can do there.
That's very interesting.
In fact, you can go see it at the Booz Allen booth. You can see actually all of this in action there.
That's very interesting. Yeah. Eric, with what NVIDIA is doing on the hardware side, how different is it, between what Bill and Booz Allen are trying to do on the defense side and what Lawrence is trying to do on the racing side?
Yeah, I want to echo Bill's comments on the value of proving out in the crucible of motorsports. If you look at conventional commercial use cases, there's so much that's incompatible with what the DoD needs. In motorsports, you have relatively low volume, relatively custom systems similar to defense. Yeah. You have a relatively cost insensitive customer compared to commercial, similar to Department of Defense, and you have highly austere conditions at times. Sort of a failure is not an option engagement process. And then you also have extreme circumstances of speed or vibration or temperature that you're subjecting it to. So, this is not a conventional commercial use case for a piece of electronic hardware. Yeah. Actually, this is what's so challenging about certifying leading edge electronics into DoD systems. And so being able to engage in this sort of testing and proving in an environment that can pull on the full volume of talent that lives outside the classified space, because this is a great challenge that the classified space is just headcount, it's low. And so to pull on all that volume, engage on surrogate problems, solve those out there, and those are surrogate problems that the commercial electronic space are not incentivized to solve. Our largest customers are data centers. It gets hot in there, but not race tire hot, right? Yeah. And so it's really useful for that, because this is outside the bounds of a conventional commercial design space.
It's also a combative environment. I mean, if you've ever raced, absolutely, you are like doing everything. You don't smash into each other's cars. You're not supposed to do that. But you are absolutely drafting each other, touching wheels. I mean, you are like in intense combat on the race
I have a
field.
pretty good idea in a data center environment that no one's banging my towers into each other. They certainly better not be. That's outside of warranty.
Yeah.
But in the motorsports arena, I mean, that's an engagement I expect. And so that's where it's really helpful to test that, because you wouldn't naturally run into that. And you wouldn't be asking your engineers to run into that. It's that's not what Google is experiencing.
Yeah. Lawrence, I'm curious, I'm sure you got into this for other reasons. Is this something a conversation you ever thought you'd be having in terms of that the things you're doing could have an impact or applicability on a battlefield, that what you're doing could be proving out, autonomy and AI systems that could be used for other methods like that?
Yeah, I mean, we race because we love to race, right? The mission statement of our company is just one word: win. And but we knew, like to Bill's point earlier, racing's always been a proving ground for the automotive industry. Now with autonomous racing, it can serve that purpose for AI. And so, competitive teams, when you're racing against the best in the world, like every ounce of performance matters, and the speed that you can extract that performance from the machines and from your software is also really critical. And so the ability to, and it's not sort of an easy thing where you're just turning a few knobs, right? The development of AI itself is extremely complicated. It takes big teams of engineers. There's a lot of a whole ton of manual work that goes into that. And so that's why, as a race team, to get the most performance from when we're on track, we have to use AI not just to drive the car, but also agentically to help our engineers understand what's happening, to understand the decisions, the complex decisions that the software is making, and then to make all of those fine-tune adjustments through all the different tool chains, the Booz expertise and the NVIDIA tool chains, all the things that go into that. There's still a ton of human work, and that's, as we look to the future, and agentic AI can come in and help accelerate those things, help us go faster, help us be more competitive. That at the end of the day is what we think is going to separate the who's on the podium or not.
Yeah, super interesting. I think if you've spent any time in this room today, you've heard the word drone probably 1,000 times, because it's such a important part of modern conflict, as we're seeing played out in foreign zones of conflict like Ukraine. We hear them over there, quite frankly. So what's the commonality? If you think of the drone as the sort of platform of choice right now as autonomous system in the Department of Defense, and then the autonomous race car, what are those commonalities outside of the obvious in that they're autonomous systems? What is there to be learned? What are the similarities? What are the differences? And again, how can there be a linkage between those two, what you would think are vastly different mission spaces?
I think you're going to see more and more drone versus drone, right? And it's very much, car versus car on the track, right? And whoever has the best understanding and can update their models the fastest is going to win. But also that whole sensory envelope, like a race driver. I mean, a Formula One race, it's basically like a drag race between corners, and whoever carries the most speed through the corners wins, right? In the end, but there's a lot of sensory perception that a human has. Trying to get that into the autonomy is the challenge, and trying to get the autonomy to understand that sensory input, right? And the same thing would be true in a drone versus drone environment, or just the whole drones have to operate in a natural environment as well, and they have to react very fast.
Sure.
I think some of the differences might be generally you're not swarming, if you like, on a racetrack. There might be racetrack drivers that work together as a team sometimes. That does happen. But still, in the end, each one's trying to win, right? Whereas in a swarm, they're going to be interoperating a lot more. But that whole physics of moving together, leveraging, drafting each other properly, is all going to be true in a dogfight. It's going to be true in a race as well.
Eric, I saw you nodding your head about the learning aspect, how these systems can take feedback and build upon that. Tell me more.
Yeah, so this is great, a great opportunity to explain the difference between a simulation and a digital twin. A simulation tries to capture as much about reality as is useful for the problem that I'm trying to solve. It becomes a digital twin when it's paired with a physical twin.
Yeah.
Twins come in twos. That should be intuitive to us. And so now there is this question, though, of what's the loop of that interaction. So if I look at it, it could be in a battlefield circumstance, or I could look at it in a racetrack analog. There's some model that lives on my edge devices out on the racetrack. Does that model learn between races? Does it learn between pit stops? Does it learn each lap?
Yeah.
So there's a relationship between my edge device and some other computing system that I have nearby. It's not tethered, but it's related to what's going on. What's that check-in frequency? How is it? Because probably it's not fully training on an edge device. That can happen to some extent, but retraining is often needs a little bit more powerful compute than you can put on a single edge device. And so what's that check-in frequency that allows it to take all of the sensor data that it's coming in? The track is changing, the tires are changing. What's the loop of that? That is a competitive advantage. If Bill's training every race and I'm training every pit stop, I will systematically outperform.
Sure.
And I won't go into any specifics, but we can all imagine, of course, that's true in the battlefield as well.
Yeah. I'm curious about resource constraints, and I know we talked about this a bit previously. On the racing side, you're limited sort of by governance that you can only use so much.
Right.
There's
no
rules.
quantum computers yet.
Yes. On the battlefield, you're limited by network, or you're in an austere environment.
Space wattage, power too, and weight. All that stuff.
There's a lack of resources. So I'm sure that's another commonality. But talk to the racing side of it first, Lawrence. How do you deal with those constraints? How do partners like an NVIDIA help you come up with better ways of dealing with those constraints? And how are you ultimately pushing in that directions for more efficiency so that you can continue to train in a way that's every pit stop rather than every race?
Yeah, so what a human does on the racetrack is quite remarkable, right? And they've learned that every time that you're on track, Bill, right? You're getting better, you're honing your skills. And if you look at like a Formula One driver, they've been driving since they're young children most of the time. So their control algorithms, all of the way that they actually operate the vehicle is instinctive to them. But then you look at an actual race, with other agents. There's a series of decisions, we call this racecraft, that the human has to make based on how their car's performing, based on how their opponents are performing. And so getting a simulation environment down where we can as closely replicate what the actual physical AI system is doing, that allows us to then go after the really hard problem, which is how does the AI make those decisions? How does it make good decisions throughout the race so it can actually win? And that's the really hard part. That's the grand challenge of autonomous racing.
And you can tell that it's important that it's a contested environment because qualifying order is not the same as race order at the end.
Right.
So racing on a track with your own systems versus in a competitive environment can produce vastly different results. And so you're not only modeling the physics of what's going on, you're modeling the decision space of other actors.
Bill, you mentioned, or you heard Lawrence mention some of those constraints. What are the analogs on the defense side? I think we know them pretty obviously, whether it's energy or network or compute and things that you can't maybe get to the battlefield. But what are some of the key ones, and how is Booz Allen helping the Department of Defense overcome those?
I think some of the big areas, for example, are these network denied and GPS denied environments that you run into as a constraint. His car can't crash if the network goes down. Right?
Yeah.
He's got to have enough autonomy locally to continue to operate. It may not be as optimum on the track when the network's down, perhaps, depending upon where he's put the training and the engines, the AI engines that operate on it. But we have to be able to operate continuously with or without the network. I mean, the first thing you do in a battle is take out the command and control and communications, right? That's what you go after. So another component is, you mentioned quantum a little bit, is at Booz Allen we're working on these quantum sensors for the IMUs so that they really know very accurately where they are during a network denied environment so that the drones can operate that. But really the accelerometers are important, all of the kinds of things that you would have also in racing, right?
Yeah.
I think another thing about racing, like I'm a fair weather racer, I don't race in the rain, but they have to race
Literally
in the rain.
fair weather.
Yeah, they have to race when you wouldn't believe though things like when you pull out on the track and your tires are cold, what a difference that makes. People don't realize how big the difference is between warm tires and cold tires, and trying to get the AI to understand that you can put a timer on and all this other stuff, but you got all the different temperatures and all those other things. I think the most interesting thing that I would like to understand how Lawrence does is you send a driver out on the track and they come back and they go, oh, the rear bearing is this, or how do you translate an AI to be able to understand that, Lawrence? That's
Well,
the feel of the car is not right.
It's a great question, and race cars just have a huge amount of sensors, right? Not just perception sensors, but also all of the vehicle dynamics and just a whole bunch of data, right? And so, in theory, you should be able to, with that data that you have, you should be able to perform better than a human that's just driving by the seat of their pants, using their intuition. But the state of the art right now is like we haven't been able to achieve that, and that's what's so exciting about the field of autonomous racing is that we're trying to replicate, these very complicated, human cognition and the adaptability of a human.
Yeah.
I know you're a fair weather driver, but I'm sure if we put you in a race car in the rain, it'd only take a couple of laps and you'd probably maybe a little squirrely, but you'd be dialing it in, right?
Yeah.
That's because you can generalize like your expertise of racing and your knowledge of racing to a new environment that you haven't trained on before.
Yeah.
And that's where we need to get to with AI to make it be effective, to do the things that we want on a battlefield, which are very complicated, and you have an adversary that's also employing AI. And so how do you update and have your AI get better and better without days of engineering and retraining, and these are the workflows that we're working on together that are so exciting for the future of any mission critical system, not just on the battlefield.
This is where the simulation space is so important as well, because we talk about the intuition that you have sitting in that seat as a driver. I don't need to ask a driver to go touch the tire with his hand to tell me. He knows the temperature of the tire because he can feel how it's catching on the track. He can feel slippage. And so the driver has an internal model that has an intuitive understanding of the relationship between the temperature of the tires and how it's gaining traction. In the simulation space, if the simulation is correct, that's how the AI model can explore the relationship between those two things. It doesn't inherently know ahead of time that they're necessarily connected. It can gain an understanding of that the same way that a driver does by testing, except that it should be testing in the simulated environment. Yeah,
the other thing about the simulation space is you can test edge cases you just can't test in the real world.
Yeah.
Right? I mean, you can apply, you could race on ice, right? You can race on, how are all these things going to happen, right? You can race with rocks in the track and all these other things. And the same thing that's very important in DoD is being able to test when it's foggy, when it's raining, during a hurricane, during all these kinds of things that you just couldn't test in the real world, right? Yeah. Without putting people's lives at risk or strenuous environments, right? And I think that's where simulation is really, really important in all autonomous systems, is being able to test all the possibilities, not just the possibilities that you can record of a driver driving, right? I think another thing that Lawrence brought out is those F1 drivers, they started on go-karts at like 8, right? So they've got so many years of that dynamics. And so to be able to catch the AI up, AI is going to require a tremendous amount of data input, and you'll only get that synthetically. You're not going to be able to run, like Tesla, for example, they do millions of miles an hour of simulation in the cloud to do training. You can't physically do that in the real world, right? But you can, he can drive millions of miles of test driving in the cloud, right? He can't do that on the track.
Yeah, like on the racetrack, we can go and calculate mathematically an optimal race line, right?
Yeah.
In theory, should get you around the track the fastest. But when we've worked on some of these human imitation learning pipelines, you put an expert human driver driving that same track, the mathematical optimal race line is not actually what gets you around the track the fastest.
Yeah.
And so that's why we've been working on pipelines to take, human inputs as a starting point and as a way to inform model development, so that we're learning from the humans as we try and get the AI to have that same level of performance.
I mean, just the tactile control of rotating a car with a little bit of oversteer around the track and not going into too much oversteer and spinning is an amazing amount of control that humans can have. And so in addition to that, you may or may not understand this, but in a Formula One car, you can go around and turn slowly, and you can go around and turn quickly. If you're in between, you crash because the aerodynamics aren't working. And so that's another thing that's really beyond the normal driver. Going faster into a turn is not a good thing on the street, but in a Formula One car, you have to. And that's hard to get. That whole understanding and trying to get that into an autonomous system is just incredibly hard.
Yeah. Well, Lawrence, I think we've alluded to it, but it doesn't sound like a machine or an autonomous car has yet beat the best humans. I don't. Maybe I'm assuming that incorrectly.
No, you're right. Like we're pretty good. Like we're better than the AI is faster than I can drive a race car. Probably you too, Bill. I don't know how good you are. But when it comes to that top expert, that F1 level of driver, it's still an unsolved problem.
Yeah. But do you anticipate you'll get to a point where it does?
Oh, I think so. I mean, I think we will, but that's not going to take the fun out of motorsport. It just adds a whole new dimension to what we can do on the track. And motorsport's about inspiring people to love engineering and to follow their favorite drivers, and all those kinds of things are true with autonomous racing. So we think that there's always going to be a place for AI racing against the humans, hopefully someday.
Well, I'll leave us with one closing question. Things are moving incredibly rapidly, thanks in large part to the NVIDIAs of the world. As NVIDIA and other organizations rapidly innovate, accelerate, and move at the pace of seconds, minutes, days, rather than these larger cycles. One, how are you doing that? And then two, how does that impact the mission or your ability to keep up with the two of the gentlemen on the either end? To kind of, I'm sure it's a great thing, but it's obviously probably a challenge to keep up as well, because it's changing things in a fashion that you're not probably used to.
Well, one of the reasons that Booz Allen has these partnerships is because we have to keep up to support our customer base, right, and the mission that we're doing. So we have to move as fast as NVIDIA to adopt what they have. We have to move as fast as a Formula One car to win on the racetrack and on the battlefield. So I think that's an important point to take away. But another thing about simulation, NVIDIA has got such a tremendous lead in chip design because of simulation.
Absolutely.
Right? They have the best simulation capability in the industry. So it's a self-reinforcing prophecy there. And their work on physical AI just changes the world.
Yeah. Eric, anything to add there?
Yeah, no, it's a great point. I would say that we keep our chip designs excellent because we invested in the simulation of chip design way back in the 90s, and that's always been at the heart of how NVIDIA does design. And then the other thing I would say is that that's within our core expertise, but when we want to reach out into verticals or systems that are outside our expertise, we stand on the shoulders of other giants. And really those are the two, and that's true in the semiconductor space as well, by the way, with our partnerships with TSMC and others. But it's true outside of that, in the automotive space or any of these vertical spaces. And so, it's really both. It's simulation, and then it's, of course, working with partners who have the expertise in their areas to work alongside us.
Lawrence, final word on this?
I would just, thanks for the support from Booz and NVIDIA. If we did manage to beat China on track last year. We hope to beat them again this year, and we're just excited to help push the state of the art, state of the practice faster, and hopefully we can have some kind of influence on NVIDIA and Booz to keep making the tools better and helping us achieve our goals on the track.
What a fascinating topic. Thank you to everyone who attended, and especially thank you to Bill, Eric, and Lawrence. Let's give them a round of applause.
Nice job.